I continue the work that we built upon with my current supervisor, Valerio Maha. So I'll be joining two projects in one. It's a clear continuation of one of the other, so I don't think you'll have any trouble seeing the flow. So the topic is cosmic shear covariance matrix comparison. And before I start jumping into the seminar, I'm going to give you a bit of motivation behind what we're doing. So basically, covariance matrices, they're among the most difficult pieces of end-to-end cosmological analysis. And we say that because they are, I want to say, extremely hard to obtain. I know some people here work on covariance matrices, so hopefully they'll back me up on this. They're very difficult to obtain, and not just very difficult, there are many small caveats. It's also very time consuming. So for real cosmological surveys, it takes a long time to generate these covariances. And also, as we look ahead, the data vectors, they will be increasing in size, for future surveys like Euclid, like LSST. The size of the data vectors, they will get a lot larger. And as they increase, the number of the elements in the covariance matrix, it will grow, it grows quadratically. So they'll become even bigger and even harder to analyze. And one of the ways that we look into for, finding a simpler method of analyzing these covariance matrices, and I want to say possibly even obtain them in an easier and faster fashion, is to use compression schemes. So they provide a simpler method of at least analyzing them. So now I want to start with the cosmic shear, which is the observable that we're using here. And we have this picture here for cosmic shear. It's very, very exaggerated. Okay, cosmic shear is in the weak lensing regime. So the angles that you see here, they're going to be a lot smaller than this. You can do approximations like sine theta equal to theta, so it has to be very small. And basically what happens is as light travels from distant galaxies to us, it will pass through various things in the universe, the large scale structure of the universe. And we know that light bends due to gravity. So as it passes through these large scale structures, light will get distorted. And we can use this distortion of light to characterize and to obtain information about the large scale structure of the universe, how the matter in general is distributed. And when I say matter, I don't mean just the visible matter. What is most important is the dark matter, where we can only obtain information about them, seeing how the light changes as well. It changes, mostly gets distorted as it comes to us from these further sources. And so in that sense, cosmic shear can be used to probe the dark matter distribution of the universe and also give us information about dark energy. Okay, so in this drawing here, there's a lot of information, but I'll pick out the ones that are most important to the seminar. And I will start with the angle alpha that you see here. And the angle alpha we can characterize it by saying that it's the gradient of the lensing potential. And this is an important quantity that will give us information about the matter distribution of the universe. The other important quantity that we have here is this d alpha hat. And as I've described it here, you can see that it's the gradient of the potential phi. And this potential phi is related to the Bardeen gravitational potentials. So you have two Bardeen gravitational potentials, which is phi and psi. But since we're considering that, this is in the absence of anisotropic stress, we can say that one is equal to the other. This goes down to general relativity. And so instead of showing both of them, we only need to consider, just one, because they're going to be equal to each other. Okay, and finally, we have the magnification matrix, which is given by this A here, which is the partial derivative of beta with respect to the angle theta. And as we see in the drawing, the angle beta is equal to theta minus alpha. So we take the derivative of that. And I have made some changes to the magnification matrix. Of course, I will have to expand it. There are a few steps in between. And we write it basically in terms of the partial derivatives of the lensing potential here. So I'm going to write 1, 1, 2, 2, 1, 2. That just means that it's the derivative with respect to theta for each one of these. So of course, there are 2 theta, you know, we're looking at angles in the sky. So theta 1 and theta 2 are going to depend on the orientation. And here I wrote the magnification matrix divided into 2 parts. And this part here is going to be its anisotropic part. And the second part is its isotropic part. So it has 2 distortions. The anisotropic one, it has a privileged direction. So it's basically the image will get distorted in one direction. So it gets like elongated, let's say. And for the isotropic part, it just it's going to be like a circular distortion. So it will just expand, get bigger, right? Okay, so we can further rewrite this. So this whole term here we'll call kappa, which is the convergence. And this first term here is represented by the shear. And here we have a rotation matrix. And this angle phi here, psi here is just the angle between the 2 components of theta. Okay, we can further divide the shear. We can write it in terms, so the shear is a 2-spin component. It's a 2-spin shear, and it has 2 components, right? Which is the tangential shear and the cross shear. And so they're related by this equation, which you can obtain from the previous one that I showed before. It's also interesting to write it in terms of its real and imaginary parts. And visually, that's what this looks like. So as I said, the convergence, it will just get bigger, you know, circular, with a spherical symmetry. And the shear, you have privileged direction. What we see in the sky is actually these 2 effects. And then of course the shear is going to be more apparent because you're taking something that's mostly circular and you're going to elongate it. So these are the 2 effects that we see. Okay, so we see that for each galaxy, but the shear and convergence of each galaxy doesn't really tell you much about, sorry for the noise, the background noise. So the shear itself, it doesn't tell you much about the distribution of the universe per galaxy. I mean, what we actually need is 2 pairs of galaxies. So we're going to be taking the shear correlation function, and we're going to be comparing how 2 galaxies relate to each other. Now, for us to obtain real information about the universe, we don't just work with 2, we work with pairs of thousands of galaxies, you know, the more the merrier. So the relationship between these shear components, for the tangential shear, it's just going to be parallel to the X and Y axis that you're used to. So this is again in the plane of the sky. And the cross components are going to be at an angle. So either this way, that way, or, you know, whatever angle you want. And then the cross components are just going to be given by this. So it's between the tangential and the cross component. Okay, and then, so the observable that we're interested in is going to be cosmic shear, which is given by psi here. So it's the correlation between these 2, the sum of the correlation of the 2 components. And you notice that I'm not writing anything about the here. And that's because in the weak lensing regime, we can approximate it to just consider, you know, the shear, because that's what's more apparent. And then, so from this first equation to the second one, there are quite a few steps. I didn't put it here, but this is available in most of the weak lensing literature. Although don't look at the papers will just give you these 2 steps mostly. If you want to know what really goes on, then you have to look into books, and I can point this out if anyone is interested. So the interesting bit here is the power spectrum. So this is the convergence power spectrum. You see the K here, which is exactly the same as the shear power spectrum. We can relate the two. And this is where we're going to be getting information about the matter distribution of the universe, or of the universe in general. So we have the power spectrum here of the density contrast. Density contrast is represented by the delta here. And in this Q function, we have terms relating to the matter distribution of the universe, H naught, and then you also have the dependence on the redshift or the scale factor, if you will. Okay, so those are that's the observable that we're using here. And before I jump into data and covariance matrices, telling you about those, I want to stop for questions regarding cosmic shear, if anyone. Okay, I'm looking at the chat. I don't see any raised hands, so I'll just go on. You'll have space for questions before I jump to the next one as well. Okay, so regarding the data set and the covariance matrices, we use two different data sets. The first analysis is done only on the dark energy survey year 1 data set. And then we talk about the next data set, which is going to be the KIDS 1000. But okay, so for the dark energy survey year 1, we're just taking information regarding cosmic shear. And it has 200 data points originally, right? It had 200 data points for Xi plus, 200 for Xi minus. And these points are divided into 4 tomographic redshift bins. That's this plot here on the left. And it ranges from 0.2 to 1.3 in redshift. And you can see that these different colors are the redshift bins. And these are further divided into 20 angular bins ranging from 2.5 to 250 arc minutes. And the angular bins, they're just these data points that we have here. And the shaded regions, they are excluded because they're representing the scale cuts. And these scale cuts are needed, unfortunately, because we are not generally able to model the baryonic physics that are relevant in these angular scales. So we can see that Xi minus is more sensitive to these scale cuts, to this baryonic physics. So it's the one that suffers most cuts. And in the end, we're left with 227 data points of Xi plus, Xi minus. So we'll be having a 227 by 227 covariance matrix. And our model is composed of 16 parameters. So we have 6 cosmological models, 2 astrophysical, I said models, I meant parameters. We have 6 cosmological parameters, 2 astrophysical parameters, and 6 systematic ones. Okay, and the second data set, is the one from the KIDS survey 1000. And again, we're only considering cosmic shear. So it has 237 data points, and this is after the scale cuts as well. And it's very similar to the DES one. It has the bins, the angular and the tomographic bins are divided differently, but again, it's very similar. So the 5 tomographic redshift bins span from 0.1 to 1.2. And we have 9 angular bins going from 0.5 to 200 arc minutes. And the angular cut, the scale cuts here are only done on Xi minus. So we don't have any on Xi plus. And we have 13 parameters, where 5 of them are cosmological parameters. We have 2 astrophysical parameters and 6 systematic ones. The 2 astrophysical parameters that I mentioned here are not the same as in the KIDS, as in the DES model. But I won't be talking about much of these other parameters later. They're just relevant in terms of the parameter constraints. Okay, so moving on, for the covariance matrices, we use 3 different ones. The first is the DES covariance matrix, and here I'm representing it by DCM, but you might see it written as FCM as well, because again, I'm combining two different papers in one presentation. And it was generated using Cosmolike, which gives us an analytical covariance matrix. And as I mentioned, it's 227 by 227. The second covariance matrix is what we're calling the Gaussian covariance matrix. And this was generated again analytically, but using the code for the Kids 1000, Kids 450 survey, which, you know, they use the same code for computing their covariance matrices. And it has the same functionality as COSMO-like, of course, but we wanted to accentuate the differences between these two matrices, because these are the two matrices that we're going to be comparing. We want to find the difference between these matrices. So we wanted to accentuate the differences. And so we only took the Gaussian part of this matrix. And again, it's 227 by 227, because all of the cosmological analysis with these two matrices are done on the same data set. So they have to be the same size. Also for comparing them, they have to be the same size. Finally, we have the Kids covariance matrix, which is the same one that kids used in their analysis, the Kids 1000. And as I mentioned, it's 237 by 237. Okay, and these are the original constraints for the DS covariance matrix and the Gaussian one. And as I mentioned, we do expect to see differences. So we don't see it so much in the omega matter, but it's present in S8. And this other parameter here, this parameter A, is one of the systematic parameters that we have. And this is common between the DS and the Kids survey. And we see that there are some differences here. And we hope to find out why there are differences in these constraints. But before we do that, again, I just want to give you guys a minute if you have any questions. If not, then I'll move on. Okay.
May I ask you a question, Tassia?
Yes, go ahead.
When you compare the Gaussian one with the DS, you have the same number of points, but they both so I'm assuming that in both you are using the same scale cut and the same binning.
Yes.
Okay, but you just change the footprint for the Kids footprint.
Yes, yes, exactly. Yeah, we use the DS one.
Thank you.
Rogério?
So for the DS, so this is only DS. You're comparing the Cosmo-like covariance matrix with a Gaussian covariance matrix for DS. Now, how did you compute the Gaussian covariance matrix? I'm asking this because in Cosmo-like, you have the option to get only the Gaussian contribution. Did you do that, or did you use another code?
Well, we didn't use the Cosmo-like one. We used the original code from Kids.
So use the code from Kids to compute the covariance matrix that you're using for DES.
Yes. So
okay,
DS is nice enough that they give us most of the information, right? The size of the survey and its depth and everything. So we had, well, so I'm not sure if this information was available online at the time that we did this. The covariance matrix was actually generated by Scott Doddleson, and he had access to all of the DS information. So he was capable of computing this matrix, which was the problem that I had. And this is why we have two different covariance matrices to compare for with the DS data, and we don't have two covariance matrices for Kids, because Kids didn't make all of this information available.
Right. No, what I'm saying is that instead of using the Kids code, Joachim's code, right? Mm-hmm. You could have taken the Cosmo-like, and just kept the Gaussian part.
Yes.
That would also give you another Gaussian covariance matrix, and then there'll be no work, basically. Just yes. And the other comment is that the differences are very small. So we checked in our covariance paper for DES year 1. So we had a whole covariance paper checking the effects of non-Gaussianity in the covariance matrix. And of course, the result, we have plots similar to these ones. And then we compared only the Gaussian part of Cosmo-like with the full Cosmo-like. And the result is this, that is not the non-Gaussian, the non-Gaussian meaning super simple covariance plus tri-spectrum. It's not really, doesn't really bring you much information in terms of constraining data. So this is what you would expect, yeah.
Yeah, no, I agree. We could have done that, but we wanted to make life a bit more complicated, right? That would have been the easy way out. Just take one code and test that. And of course, this is what we're hoping for as well. You know, when I present our covariance matrix comparison scheme, then we hope that people will be doing that using their own code. You know, you can generate different covariance matrices and you can compare them using our comparison scheme. But yeah, we wanted to make this we wanted to be as thorough as possible. So that's why we took a different code, generated a covariance matrix using a completely different code to show that this can be done as well.
Okay, thank you.
Sorry, Roger, I guess that was my confusion. So in the last slide, what is kids for the Gaussian is just the code, right?
Yes.
Okay, sorry.
Okay, so let me move on then to the, if there are no other questions. Okay, so I'll move on to the compression and the transformation methods. And so the first thing that we did before comparing these matrices was what do we need to compare exactly? We have 227, we started off right with a 227 by 227 covariance matrix, and that's a lot of elements, even if you just consider the independent elements, because as we know, covariance matrices, they're symmetrical, so we don't have all that many elements. It's basically n times n minus 1 divided by 2. That's where n is the number of the size, the dimensionality of the covariance matrix. So it's going to be less, but then, you know, it's still a lot of elements. And if you consider that these data sets are going to be getting larger, then, you know, we can have like 1,000 by 1,000, even larger covariance matrices. Do we really need to compare all of those elements? Should we only be looking at the diagonal elements, you know, that are usually the highest? Where do these differences lie? So we started off trying to pinpoint where the differences are and which parts we should be comparing. And we started doing that using, so we started looking at the eigenvalues and the signal to noise ratio, which is the simpler thing that you can do with a regular matrix. And so we identified the 200 lowest eigenvalues. We set them to something close to 0. Wasn't 0 exactly, because then you get a semi-positive covariance matrix. So we set them to 8 orders of magnitude lower, these values. Sorry about that again. The sneezing. So we set them to 8 orders of magnitude lower. So just so we could keep the covariance matrix positive definite. And then we obtained a different covariance matrix, right, with these new eigenvalues. And we run a full cosmological analysis on that. And we repeated the same process for the signal to noise ratio as well. So we took the modes with the 200 lowest signal to noise ratio. We got rid of them by setting them to something even lower. And then we run the cosmological analysis. We did that with the highest signal to noise, with the 200 modes with the highest signal to noise ratio as well. But we don't usually show these results because they're similar to the ones that we have here. And so this is what we get for these two procedures. So we see that the constraining power is largely lost for S8 and the intrinsic alignment parameter. For the omega matter, this is for the eigenvalues, it fares worse than for the signal to noise ratio, for example. So this is clear to us that this isn't where we want to be looking at. You know, we shouldn't be looking at the eigenvalues or the signal to noise ratio at all. If you're only interested in omega matter, for example, then maybe you shouldn't do such dramatic cuts on the signal to noise, and then, you know, these constraints will be better. But again, so you need to be careful. Do we want the full parameter space? Do we only want omega m? you know, and omega m fares better here because it's the parameter that has the highest signal to noise in the data. So, and the other ones don't. So when you do the raw cuts, the raw signal to noise cuts, you're going to be losing modes with a high signal to noise for the other parameters as well. The only parameter that, the only parameter that really does follow the tendency for the signal to noise ratio, it's a line like this, and you know, is omega m. So the moment that you cut the 200 lowest signal to noise, you're essentially taking out the 200 lowest for omega m, and that's not the case for the other parameters as well. And so before I go on about that, I want to talk to you about the KARHUNEN-LOIVE decomposition that we did as well. And this is, I'll just abbreviate it to the KL decomposition. And this is basically a tomographic compression. And again, what it does is it finds the eigenmode that has the highest signal to noise contribution, and it transforms the 2-point function of this eigenmode into real space. So since this tomographic, this compression is done with respect to the tomographic bins, we don't use the 227 by 227. We use another covariance matrix, a 190 by 190, where the cuts, they're consistent between the angular, the tomographic redshift bins. And so, okay, we have a 190 by 190. If we take just one KL mode, which is, you know, the one with the highest signal to noise contribution, then you're going to have a compression down to 19 by 19. But you can use more modes for the compression, then it's going to get bigger and bigger, which is not what you want to do, because if you're looking for compression, you don't want to use a lot of modes. So maybe take the first, the second, the third, and see where that goes. And so we did that, and the results for these, as I said, with only one KL mode, so for the highest compression that you can get, the results, they're not much better than the ones that I showed before, especially for S8 and the intrinsic alignment parameter A. Now, if you add another KL mode, you see that omega m, the constraints are better reproduced. But again, that's not the case for S8 and the intrinsic alignment parameter. And that's because the information for the intrinsic alignment parameter is mostly contained in the modes with low signal to noise. And again, if you're interested in the S8 parameter, which has a large degeneracy with intrinsic alignment, as we see in this plot here, then you want to be careful with the compression that you're choosing. So we see that choosing a compression that relies on signal to noise might not be the way to go. And the results that I'm showing here, they're, well, to be honest, they're really bad. But you can trust me when I say that the KL decomposition, it works in a lot of cases. There are many papers that use it, and they're able to reproduce the parameter constraints well. But again, this wasn't the case for us. So if you're looking for a compression scheme, don't check just the parameter that you want. Be sure to check all of the parameters, because you might be removing information that's necessary. Okay, so finally, we have the MOPED compression scheme, which is a massively optimized parameter estimation data compression. And this is very popular in the literature, and it compresses the data vector and the covariance matrix down to the same dimensionality as the number of free parameters. And this is the compression scheme that's most extreme. So it doesn't matter the size of your covariance matrix. You can have 1,000 by 1,000. It's going to compress it down to that same number. So and in our case, we have 16 free parameters, so it's going to go down to 16 by 16 covariance matrix, which is a very large compression. And the weighting vector, it's chosen in such a way as to maximize the Fisher information matrix. So what we have here is the weighting vector given by this B that I call, and this comma here is just your general derivative. So it's the derivative with respect to alpha, where alpha is the parameter that you're interested in. This is only going to be one row for one parameter, but then of course we extend it down to our 16 parameter space. So it'll be 16 times the size of the data vector. And this mu here is a fiducial value for your cosmology. So if you want to compress it for omega m, for example, you're going to choose a fiducial value of omega m. And what we do here is a bit of cheating, because we already know what the best fit value for the parameter is. So we compress it, our fiducial values that we take are the best fit values for the parameters, but you don't exactly need to do that. But since we had this information, we decided to use it. And then you derivate it for your given parameter, and then C is your covariance matrix, so the full covariance matrix. And then you apply that to your data set, and here X is representing the data set. And then, again, if you're only using one parameter, then this will just be a number. And then your compressed covariance matrix will only be a number as well. But since we have 16 parameters, or 13 in the case of the kids covariance matrix, then it compresses it down to 16, and the compressed covariance matrix will be a 16 by 16 covariance matrix. And the impressive bit is that we're actually able to reproduce the parameter constraints quite well. So this is for the original covariance matrix, which is the DES one, but the results are similar for the kids covariance matrix as well, in the sense that you have my resolution here is not so good that you can clearly see 2 lines, but they're superimposed here. You have 2 curves here, and it just shows how good these parameter constraints are. And then in the sense of covariance matrix comparison, this is also very helpful. And FCM is basically your DES covariance matrix, and GCM is the Gaussian one. And for the full covariance matrix, the one-to-one analysis, which is honestly something that we don't really do because so many elements here, you see that there's this large region of disagreement. It is true that these are the smallest elements, okay, and we don't generally look at these smallest elements, but we do see differences in the parameter constraints. So this might strike you as important if you're looking for the differences. These red dots here are going to be the diagonal elements, and we see that there's some slight differences. But again, looking at the full covariance matrix, the elements of the full covariance matrices, it doesn't give you a clear picture of which elements you should be looking at. Whereas if you look at the one-to-one analysis for the elements of the compressed covariance matrix, then it follows a clear tendency. You can relate this one. This point here is somewhere here. So it looks a lot different if you're plotting it like this. This is log plot. This isn't. That's why it's far off. It's not that different. And this shows you a clear tendency that you can compare more easily with the true results that you obtain. Okay, so that's it for the compression scheme. Now we move on to an invertible transformation. And why did we look for an invertible transformation? We've already found, a good compression scheme. Why do this? Because the compression scheme, it's non-invertible. So once you have the compressed covariance matrix, you're not going to get a full covariance matrix from that. So what we do is we take the compression scheme. So this is the invertible transformation. We took the old compression scheme, this V, and we extended it down. So we added this U matrix here, just so we could have, so the compression scheme before was 16 by N, where N for the DES covariance matrix is 227. And this, for it to be invertible, it has to be square. So this new capital B here is going to be 227 by 227. So you're N by N. And it's going to be invertible. So, we can go from the full covariance matrix to the compressed one and then back again. And okay, so you had your 227 by 227. Now you have another one. Why would you want such this other covariance matrix? I mean, I thought the point was, compressing the information, but it does get compressed because the way that we choose B, we choose U in such a way that the off diagonal elements, they're 0. So we don't worry about that. U is just going to be the null space of B. So we see that here. And this other matrix here, if we look at this new covariance matrix blockwise, so we call it C3, is going to be completely irrelevant for the parameter constraints. And I'll show this to you in a bit. So we have reproduced the MOPED compressed covariance matrix, which is given by C1. And we have a bunch of other elements that we don't care about, but you can go back and forth between C1 and your full covariance matrix. So to prove to you that C3 really doesn't matter, we went crazy with it. So we did tests both on the DS covariance matrix and the kids covariance matrix as well. So I'll go in no particular order. For the kids covariance matrix, we transformed it, and then we took C3 and we replaced it with the identity matrix. So this is a very dramatic change. We have these elements, most of the elements we set to 0. We didn't do that before, remember, for the eigenvalues and the signal to noise. We didn't do such a dramatic change, but here we set most of them to 0, and we take the diagonal elements of C3, we set them to 1, and we looked at the constraints, and you see that there's not much difference. We can even call this difference, we can say that this difference could be due to user error. So if I'm to run 2 cosmological analysis with the kids data and covariance matrix, I might see some differences between them. And same cosmological analysis, same data set, same covariance matrix, same everything, same priors, and it might give us some slight differences. So we can just write this off as user error. And this is not my word. This is Scott Dodelson's term for these differences. And then we did some similar crazy things to the DS covariance matrix as well. So we took the transformed one. So we're only changing C3, and we introduced errors of 5, 10, and 50%. And these are the results here. So again, there's some fluctuations here, but nothing too serious, nothing too bad. And then so we run the errors again, we perturbed it again, but then this time we went back to the original parameter space, data, to the space of the real data. So for these results here, we are taking covariance matrices that are very, very different from each other. They have elements differing by several hundred orders of magnitude. And we're using the original data set, and we see that there's virtually no difference between these constraints. So I hope I've proven to you that you can have covariance matrices that differ by several orders of magnitude, and the constraints are the same. So this isn't the way to go. If you want to compare covariance matrices, then you shouldn't really be looking at the full set. You only need to look at C1. That's where the information is. That's what you need to be comparing. Because if you look at the elements of the original covariance matrix, it might be very misleading. Okay, so finally, on the front of covariance matrix comparison, so this is my most recent work with Valerio, my supervisor, Valerio Maha. And so the comparison is basically done on the C1 covariance matrix, so the MOPED compressed one. And we take the 2 matrices, which we're calling C-base and C-test. This is just nomenclature. And what we actually use is the DS compressed one and the Gaussian compressed covariance matrices. And the analysis is then divided into 2 parts. We look at the differences in the diagonal elements and also in the independent elements of the correlation matrix, so the compressed correlation matrix. And the algorithm is based on a Monte Carlo analysis. So we basically, for each one, right, we take, for the diagonal part, for example, we take a mock sample. We generate many mock samples of size M, where M here is your step, let's say. So for Monte Carlo, you have a number of steps, and that's represented by the size of the mock sample M. So we perturb it given an error percentage delta. So and delta for the diagonal part is is taken from a Gaussian distribution, centered 0, and then if you need like 5%, that's going to be your sigma. And then it's just simply obtained like this. So we just add the error, that's fine. The diagonal elements are going to be squares, so you don't really have to worry about much. This is going to be squared, so it's going to be positive. You don't have to make any hard cuts. Whereas for the error in the correlation elements, we do have a larger constriction, which is that it has to be between -1 and 1. So we could just take error from a Gaussian distribution, then, you know, make hard cuts on -1 and 1, but that wouldn't be pretty. So we use instead the hyperbolic tangent function, and that's corrected for the Jacobian as well. And here I'm showing a plot for the hyperbolic tangent. So this is just the x equal to y line. And in blue, we have the hyperbolic tangent function. So if we take the error around here on this blue line, it falls more smoothly on the original element. So we take the error on the tangent, hyperbolic tangent, and then we take its inverse to be, sorry, here there should be an inverse here. So that's this is all different actually. Sorry, there should be an inverse here, and this C no, sorry, the C here is then for the element of the correlation correlation matrix. Okay, so this is never going to go to 1 because there's an asymptotic limit here, but the point is that the perturbation falls more smoothly. You know, there's no hard cuts here. Okay, so once we have that, the mock samples for a given percentage, we compute the sample covariance matrix. So this is going to be a very big covariance matrix because it'll be an M by M covariance matrix. So if we want to do a proper analysis, we're going to have a lot of numbers, you know, a lot of steps. We take about more than 5,000 to show proper results. So this is a 5,000 by 5,000 covariance matrix. And we use that to calculate a fiducial chi-square distribution, which is given by this. So this is going to depend on the delta that you're using. And then we calculate the another chi-square using the elements of the actual covariance matrices that you're testing. And then the only thing that's going to change here is the sample covariance matrix. And then, so we want to minimize the error that we're getting such that the chi-square here is going to be the maximum at the fiducial chi-square distribution of the previous slide. So we run the code for that, we test them, we obtain this value, and then we don't just want one value to show you, we like distributions. So we take the two values, the interval that we show you is the 68% probability interval. So it's going to give you like a plus minus there. And so to run this algorithm, we use LMFITs. This is again a Python code. And we define the default to use Powell's method. So LMFIT has several methods that you can use. We tested a few of those and we found a better convergence for Powell's method. So this is the one that we recommend. And then, just for trial runs, we can take M to be smaller, about 1,000. And this makes the code a lot faster. You can get results in less than 5 minutes. But for robustness, we recommend that the setting be over 5,000. So for the results that I show, it's we set M to 1,000. Okay, and the results that we have, so they're divided into the diagonal and the correlation error. And so for the diagonal parts, they differ by 2.6 plus minus 0.2, and the correlation elements is 7.8 plus minus 0.1. And just like that, these numbers don't mean very much. Okay, what do they tell you in terms of parameter constraints? Because that's what we're interested in. That's what we're trying to do. And we related here. So just to give you an example, for the better constraint parameters, omega m and S8, the differences are of about a percentage for the mean values. So the shifts in the mean values. Whereas the contours, they're about 1.4 and 2.7% larger. So we see that this is within the order that we found, the differences that we found. So about 2.6. And again, if we look for at the 16 parameter space, then the mean values that will differ by about 8%, and the constraints are about 2.6% larger. So the values that we found, for the correlations, they said an upper limit for the mean value differences and an upper limit for the change in the size of the constraints. Okay, so finally, the conclusion, we see that the algorithm is reliable. You know, it was able, surprisingly, it was able to, well, not so surprisingly, you know, this, sometimes we get good results. We were able to reproduce really well the differences in the parameter constraints. And another good thing about it is that it's remarkably faster than running a full cosmological analysis. Of course, it'll never replace a full cosmological analysis, but the algorithm that I showed here, it only took about half hour on my laptop computer. On other computers, it might take less. Whereas for a full cosmological analysis, I don't dare run it on my computer. I run it on a supercomputer, NERSC to be more exact. And it takes me about 4 to 6 hours for this cosmological analysis with only cosmic shear. And 4 to 6 hours using parallelization and, you know, many nodes. So yeah, that's the end of my seminar. I'm open to take questions.
Thank you very much, Tassia, for the excellent seminar. Now we have time for questions. If you joined us on YouTube, you can put your question in the comment section and I will read it to Tassia. And if you joined us on Zoom, you can ask it yourself. So, questions? Go ahead.
It's just, I probably missed it, but so you can reduce the covariance matrix and get using these reduction methods. And then what I miss is the reduction of the data vector. You also reduce the data vector?
Yes. Oh, so we reduced the data vector just so we could run the constraints on the compressed set. So we don't here.
But then the covariance matrix, when you reduce the covariance matrix, I see. Okay. Okay. So somehow you're also throwing data away because they're not, say, sensitive or relevant. Okay.
Well, not throwing it away. It's just a linear combination of the data. We throw it away when we do the hard cuts on the signal to noise ratio, for example. But here it's just a linear combination of them.
Right, but then, but you're reducing the dimensionality, or it's just a linear combination? So it's not okay. So it's not just a linear combination of the data. You're actually because the dimensionality changes. So it's not only linear combination, something else.
No, but sorry, what I meant was, you know, when we do the hard cuts on the eigenvalues and the signal to noise, we literally throw away information. You know, there's no the only thing that we're looking at is whether these values are arbitrarily high or low. And here we're not making such hard cuts. You know, we're just trying to maximize the Fisher information matrix. So of course you do lose information because it gets the size gets smaller. So, but so if your data is Gaussian, actually, if your covariance matrix is Gaussian, this method is said to be lossless because the Fisher information matrix will be the same for the compressed and the full data or your full covariance matrix.
Okay, thank you. That's impressive. Thank you.
Thank you, Rogério. More questions?
Hello, I have one question. First of all, that's a great work. Very nice job, Tassia. Thanks for the presentation. My question is quite related to what you've just said. Is it possible to apply the same technique to non-Gaussian covariance matrices or non-Gaussian likelihood, for instance?
Yes. So we do that for the DS covariance matrix, which is non-Gaussian.
Oh,
right?
Sorry.
And also for the kids one. Go on.
Sorry. I mean non-Gaussian likelihood. Sorry.
I don't know if this has been tested for non-Gaussian likelihoods. I'm not sure, because we usually use Gaussian likelihoods, right? So I'm not sure what you would get if it was non-Gaussian, because everything, I don't think you could use this method. I don't think, I'm not sure, because we use so to obtain the Fisher information matrix, we need the likelihood function, right? And then of course we assume Gaussianity for all of this, Gaussianity for all this. So you might have to have some more corrections if your likelihood is non-Gaussian. This might just be like a first order approximation, but you might not be able to get such nice you might not be able to reproduce the constraints quite as well.
Thank you.
Ugo has his hand raised.
Yeah, it's Ugo. Go ahead.
Let me see. Can you hear me?
Yeah.
Nice. Hey, Tassia. First of all, thanks a lot for the nice presentation. And probably you already said that, and I didn't get it. It's my question is just on the KL decomposition, the KARHUNEN-LOIVE decomposition. You were doing that on the pixel level or on the CLs?
For the CLs.
For the CLs,
yeah.
And then you somehow translated that to the correlation functions.
Yeah.
I mean, the KARHUNEN-LOIVE compressed or not projected CLs. You then somehow projected also to the. Is it? Do you have a sense if it is expected to behave the same if you only work on the configuration space side? I mean, as far as I understand, people also do this KARHUNEN-LOIVE only on configuration space, like doing on the pixel level. Now, like, I don't even know how to say that, but it's like doing KARHUNEN-LOIVE on the pixelized field for the computation of the correlations function, something like that. I don't know. Did you try that? And do you have a sense of it should give the same? Or?
We didn't try that. We actually followed the procedure in David Alonso's paper. So we had 2 papers with this, and so if we were to go down to the pixel level, I trust the method, so I'd say we get the same results. But you mean this might be better, right? If we do it at the pixel level.
I'm not sure, you know. I just wondering if you have a sense on that, you know. I was just it seems something interesting to try. I'm completely sure about that, but yeah, I was just confused if you were doing that or the other, and if it works to do something, some kind of comparison of that.
So that might be interested, but I'm not really sure if it will.
You expect the thing to basically give you the same kind of conclusion, because this is
yes, hopefully.
And then, because then thanks for putting this figure. It's also, if I'm getting the things right, what you're trying to say here is that you should go to like the highest KL modes in order to like retrieve the information from intrinsic alignment, something like that. This
not
is
the highest. So the highest is only going to capture mostly omega m, right? Because that's the one with the highest signal to noise. But if you want to capture information about intrinsic alignment, then you need to go down to the modes with low signal to noise as well. But then if you're going to include that, then you have no proper compression.
Yeah, sorry, it's like inverted in my mind, but yeah, it's like then you should go to the lowest. That's the key point. Okay. Now thanks.
But if you look at the plot for the so David Alonso has a nice plot where he shows in his paper where he shows how they look, the KL modes. And for the first one, it's a lot higher. And then even for the second one, like you start getting a more broader curves. So something like this what is this, magenta? This magenta line for the first KL mode. And then if you go to the second one, it might look like this second magenta line. And then the third one, it starts to flatten out. So it makes sense for you to only want to keep the first and maybe the second one. But, you know, why will you keep other ones if you know that it's not going to give you more information?
Yeah, I see. And then you
like it falls down very rapidly.
Yeah, it makes sense. And you expect that, and sorry, I'm not that familiar with this work from David. But then he compares with the pixel-based KARHUNEN-LOIVE. No. Okay.
So I can give you the link to it afterwards, and I can show you the plot that I'm talking about.
Yeah. Thanks a lot. That would be really helpful. But yeah, thanks. I was just confused if you were doing this pixel thing or the CL thing. And
yeah. No, but so David's plot is just a motivation of why you will want to take maybe just the first KL mode or the first and the second, and why you don't want to go down to the other modes as well.
It's completely consistent with what you're pointing here. Yeah, I see. No, thanks a lot.
Sure.
Really nice presentation.
Thank you.
Thanks to you.
Thank you, Hugo.
Posso falar rapidinho?
Pode sim. Seu microfone está baixo.
Ok, melhorou?
Ok.
Eu só queria dar parabéns à Tassia e desejar a ela uma belíssima apresentação, defesa de tese, daqui a 2 semanas. E que depois volte a trabalhar com a gente full energy, tá ok?
Obrigada. Eu espero que a banca também pense assim.
Olha, você já passou por uma banca aqui, então você já está totalmente preparado. Tá, obrigado, tá, Tassia, por ter vindo, tá?
Obrigada, gente, pelo espaço, pela oportunidade. Um monte disso daqui vai ser usado na apresentação da tese também, então é um bom teste.
Bom treino, né?
É.
Então tá. Tchau, Tassia.
Obrigada.
Okay, I think we can now wrap this up. I'd just like to say that the video will be available in our website, on LIneA's website, and also on YouTube. And thanks again, Tassia, for this amazing presentation. Thank you very much.
Thank you, Rodrigo.
Okay, so I hope to see you all back again on our next webinar. So stay safe and have a great day.